So with this video, we're going to continue talking about some probability stuff for Algebra 2. Specifically, we're looking at CC.3 to start with, and then we'll talk about a second one about combinations and permutations. We'll talk about that when we get there. But we're going to start with something called the counting principle. So let's start by reading through this first question, and then we'll talk about kind of the thought process as we go. It says Quincy just moved from Mexico City to Moscow and needs to buy a complete set of winter gear. The store has 3 kinds of parkas and 2 kinds of snow boots. If Quincy buys one of each item, how many different sets of winter gear can he buy? So essentially, we're thinking about how many different options we have here, kind of different assortments that we can make. The counting principle is essentially we're going to make a space or like a section, an outline for each thing, quote unquote, that we're picking out here. So that would be like parkas and snow boots in this case. And then we'll kind of add numbers in. So we have 2 different, like I said, things here, the parka and the snow boots. So what we're going to do is we're going to make 2 spaces. And anytime we make these spaces, we're going to assume that they are multiplied together. So from here, we need to fill in the spaces. So let's say this is representing the parkas, and this is representing the snow boots. How many types of parkas can we pick from? 3. So that's what we're going to put in this space. How many different types of snow boots? Well, there's only 2 different kinds that Quincy can pick from, so we're going to put a 2 here. Now that we have all of our spaces filled in, we can actually attempt the multiplication. This is probably not the challenge of the problem, just 3 times 2 giving us 6. But that tells us, once we have all this filled in, how many different sets of clothes we can make, how many different combinations we can get here. So 6 different sets of clothes. Let's talk through this one. It says Shelby is ordering a salad for lunch. There are 6 lettuce mixes. Okay, so this is one of our, like I said before, just things. Doesn't really change the counting principle based on what we're talking about. That's one thing we're taking into account. There's 6 lettuce mixes to choose from, 2 meats to add. For the dressing, Shelby has 8 options. So this is dressing. How many different salads can Shelby order? So the counting principle is basically a way for us to jump to this final answer without having to think of, okay, we can have lettuce mix 1, meat 1, and option 1. Or we could have lettuce mix 1, meat 1, option 2. We don't have to sit there and count out each of those things. We underlined 3 different, like I just said, things here. Things that we're taking into account. So I want 3 spaces, unlike the first one that only had 2. We said in between each of these, we're going to assume that it is multiplication. So that's why I'm putting the dots there. And then we have to fill in with the appropriate number. So let's say that's lettuce, this is meat, and then this is dressing. Okay, there are 6 lettuce mixes, 2 types of meat for the salad, and 8 types of dressing. From here, this is where we would want to multiply all those together. So we're going to do 6 times 2 times 8. Don't worry, I'm typing in on a calculator myself, so if you can do it in your head, you're above me. And that's going to be a 96. So definitely a good thing we don't have to sit there and count out each option, because we'd have to do that 96 times. There's 96 different variations we can make. 96 different salads with these different options. Okay, so let's keep going. A lot of these are similar, so after you get the idea for 2 or 3, it should kind of make sense to you. This one says, Wyatt works at a stable and is getting a horse ready to ride. There are 8 saddles and 3 saddle blankets in the tack room. Using exactly one of each item, how many different ways can Wyatt prepare the horse? So we only have 2 things underlined. We're going to multiply them together. We have 8 saddles and 3 blankets. So if I multiply those 2 things, that would give me 24 different variations to prepare the horse. Let's skip ahead and see if there's any real changes here. Like I said, that's kind of the same idea for each one. I don't know if they really get any more difficult other than just adding more options. It really wants us to do this Mr. Howard or Mr. or Mrs. Howard problem. I wonder if this is the guy that like made this IXL or this is the girl that made this IXL. I don't know. Let's attempt it and then we'll move to the other IXL. It says, oops, got to turn the brightness up a little bit. There we go. Miss Howard is hiring teachers for the science department at a new high school. There are 7 biology teachers, 5 chemistry teachers to choose from. For physics, Grayson has 5 options. Lastly, there are 5 options or possibilities for earth science. How many different ways can Miss Howard hire a staff that includes 1 teacher in each subject? So we have biology teachers, chemistry teachers, physics teachers, I underlined the 5 here, same thing, and earth science. So those are 4 different things here. 1, 2, 3, oops, we can do that a little bit better. 3, 4. So we're going to say this is biology, chemistry, physics, and earth science. So with biology, we have 7 options. Chemistry has 5. Physics has 5, and earth science also has 5. So I'm going to go back to my calculator and I'm going to multiply all 4 of those numbers together. So that's 7 times 5 times 5 times 5. And eventually we get 875 different ways or variations, possibilities, options, whatever you want to call it, that we can build this teaching staff. So with that, we would go 875. I definitely forgot the number for a second there. Let's see if the challenge problems change at all, and if not, we'll go to the next one. Okay, so it's looking like the same thing. It's different activities for crafts, sports. Okay, same idea. Let's look at the next one. And you see I already have a formula written out here. So this talks about combinations and permutations. So essentially, if order matters or not. When you see the C right here, that setup means combination, and we use this formula. If it's a P, we are talking about permutations, and that's a little bit easier to deal with. That's why I don't have that one written out ahead of time. So we see with the setup, we call the first number before the C in, and the one after it R, and we're going to plug those numbers into this formula. So let's go ahead and do that with our 4 and our 3. If we do that, we're going to have division. The in value in this case is a 4. So we're going to write, maybe I can type it in there and that might be better. 4. That explanation point, we call that a factorial. If you haven't dealt with that in math before, we can talk about that in a second. Let's move this a little bit closer. Or let's move our line a little bit closer. Something like that. And then on the bottom, we're going to have 3 factorial, and then n minus r, so 4 minus 3, that would be 1 factorial. So a factorial is basically a shorthand version of writing whatever value's in front of it times all the numbers after it. So what I mean by that, 4 factorial is the same thing as doing 4 times 3 times 2, technically times 1, although that's never going to change the number. So this and this are the same thing. So if I want to rewrite this, what I could do is I could write out that 4 times 3 times 2. We'll put the times 1 over 3 factorial is going to be 3 times 2 times 1, and then that gets multiplied by, put parentheses there. Oops, that looks weird. Let's try that again. 3 times 2 times 1. Okay, and then with a 1 factorial, it's just going to be a 1. We'll type it for this one, but if you think about it in the future, multiplying by 1, no matter how many times we do that, it's not going to change our answer. And then finally, if we start to actually do the multiplication here, 4 times 3 is 12, times 2 is 24 on top, divided by 3 times 2 is 6, times 1 is still 6, times 1 again is still 6. So I would have 24 divided by 6, and then when I divide those things, I should end up with 4 here. So this is kind of like saying we have 4 things and we're going to make a combination of 3 of them. And there's 4 ways to do this. Awesome. Okay. So let's erase here. I want to leave that formula up so you guys can see it. So I don't want to clear the whole screen off. So we'll just get rid of the stuff for that specific problem. Okay, so the permutations with a P there, that can be handled pretty similar to what we did with the counting principle. Basically, we're making spaces. This R value on the right here, that tells me how many spaces to make. And then this value tells me basically how many things I have to pick from. So if I have 3 things to pick from and they're going to go in 2 spaces, in the first space I can put, oops, this is still a line, I can put 3 things. If I already put something in this space, there's only 2 left to go in the next one, and then those would multiply together like before, and I would get 6. Let's talk about permutation a little bit more because we went so quick through that. Think about if you had, if I was in my classroom and I had, we'll use the same numbers for this case. Let's say I have 2 desks to put students at, but I have 3 students that need desks. Basically, when I go to, let's draw some stick figures real quick. Why not do some art? Really big desks or really small people, I don't know. One of them's arms aren't great, but that's okay. So I have 3 students that need desks. I only have 2 desks to give them. Let's say in this space, let's say this student goes and sits here. Well, now when I had 3 options and I put one of them here. That's where this 3 comes from. When I go to fill in my second desk, I now only have two choices because this middle person's not going to sit at both desks. So that's basically what we're doing by counting down here. So let's say this person gets it. This final number, the 6, tells me that if I have this situation, there's 6 different variations or ways, options, in which I could have sat those students. So that's what we're talking about with permutations. Just wanted to get into that a little bit more. So it's ordering things, people, whatever, in certain spots, basically. And that is when order doesn't matter. Like, it just mattered whether or not they got a desk. Combinations require a formula. They're a little bit more complicated to think about, because that would be treating the desks as different desks. Like, it was different if person B got desk 1 versus desk 2, and that's not really what we cared about in that situation. So that's kind of the difference, if the order matters or not. If desk 1 is different than desk 2, or if it's all just a desk. Okay, we'll keep going. Okay, so we're back to our combination formula here. Remember, n is the first number, so 4. R is the second, so 2. Let's kind of type this out. So I'm going to have 4 factorial on top, or 4 times 3 times 2 times 1. If you have like a TI calculator or something like that, a graphing calculator, they should have a factorial button on there. You might have to go like to the math option or something like that. If not, you can just plug this in. R is going to be 2 factorial, or that's just going to be 2 times 1, and then times 4 minus 2 is 2, so we're going to have 2 factorial again. When we start to actually work this out, though, we had this last time we had a combination. 4 times 3 is 12, times 2 is 24, times 1 is still 24. Divided by, just because this is parentheses and these are like the dots or asterisks or whatever, it's still all multiplication. So we have 2 times 1 is 2, times 2 is 4, times 1 again is still 4. So if you plugged all that in, you would just end up with 4 on bottom. When I do this division, kind of the inverse of last time, I would get 6 there. 6 different combinations. So that would be like I had, think if I had like 2 desks and 4 people to sit there, but we had desk 1 was different than desk 2. Like there were different collars or something like that. Something to tell them apart. Okay. For permutations, like I said, we can kind of use similar to that counting principle. There's 2 spaces. So let's say they're letting 2 people into the movie theater, basically. But there's 7 people that want in. So for the first person through the doors, there's 7 options of who that person could be. After that, if they're like, okay, we have room for another person, that first person doesn't count anymore. So that's why this is now a 6. I'm going to have a blocky 6. Boom. So order doesn't matter there. Whoever gets chosen there, they make it into the theater. Now, if the seats were up for grab or something like that, then it would turn into a combination. So that's kind of what we're thinking about here. Okay, so if I multiply those together and get 42, super. Pretty sure it just kind of goes back and forth like this. Let's do like 2 more just to be safe. Let's clear this. However, we have 2 spots again. So 2 spots. Let's say 2 people make the basketball team. We have 2 spots left out of these 5 people who are trying out. This is just for like who makes the team. So out of these 5, one of the 5 gets the first spot. He's not going to take up both spots, so one of the remaining 4 gets the second open roster spot. So that would multiply together and give us 20 different ways that we could pick those 5 people. Now, if those spots were point guard, small forward, center, something like that, or like varsity, JV, something like that, then it would start turning into a combination. So that's why that gets a little bit more specific. Let's jump ahead and see if it changes at all. Let's do one with 1 here, because to my knowledge, it's just kind of like a trick one. So ignore that for a second. 1 spot, 16 options. So let's say you're shopping for apples at Walmart or something like that. You only want 1, and there's 16 apples sitting in the bin to pick from. It only matters if it goes into your cart or not, basically. So there's 16 options for that spot. You've already decided you only want 1. There is no second spot or anything like that. So there's no 15, 14, nothing more that we need to keep multiplying together here. So should just be 16 here. 16 different ways. Awesome. Okay, so my suggestion then, since it seems like it's just going back and forth between combinations and permutations, take a look at this formula as you're working through this. If not, you should be okay to do something like this, similar to a counting principle. So if you have a C, it uses this formula. If that is a P there, you make however many spaces, and then you fill them in, and you just count down 1 each time. Okay, hopefully this helps you guys. Feel free to leave questions in the comments, and we'll continue with this stuff moving forward.